Welcome back. This video will cover kernel memory and uses OS/161 kernel memory space as an illustration. We would like the kernel to live in virtual memory, but there are some challenges. The first challenge is bootstrapping. Since the kernel helps to implement virtual memory, how can the kernel run in virtual memory when it is just starting? The second challenge is sharing. How to copy data between the kernel and application programs? How can this happen if they are in different virtual address spaces? The solution to the bootstrapping challenge is architecture specific. The solution to the sharing problem is achieved by overlapping kernel memory with process virtual memory. Note that when user application tries to modify kernel's data structures, memory protection or read-only exception raises, not invalid address exception. MIPS uses 32-bit virtual address, so the virtual memory is 4 GB. We divide the virtual address into half. User program resides in KUSAG, which is 2 GB. Then we divide the upper half of the virtual memory into 3 parts: KSAG 0, KSAG 1, and KSAG 2. Kernel code and data structures live in KSAG 0. KSAG 0 is 0.5 GB. It is mapped to the first 512 MB of the physical memory, so its physical offset is 0. And to translate the virtual address in KSAG 0 to physical address is simply V minus the starting address of KSAG 0. Devices are accessed through KSAG 1, which is also 0.5 GB. It is also mapped to the first 512 MB of the physical memory. By accessing the same portion of the physical memory, the kernel and the devices can communicate. KSAG 1's physical offset is also 0, and to translate virtual address in KSAG 1 to physical address is simply V minus the starting address of KSAG 1. We don't use KSAG 2 here. Both KSAG 0 and KSAG 1 are unmapped and uncached. TLB is used to translate virtual address in KUSAG to physical address. Physical memory is divided into frames. Kernel creates a core map to keep track of which frames are in use and which frames are free. Page-to-frame mapping will be different for each process. Mapping is controlled by the kernel. Note that virtual address can only be mapped to exactly one physical address, but this is not the case for physical address to virtual address mapping, because we have ksec0 and ksec1, which are directly mapped to the first 512 megabytes of the physical memory. So we have more than one possible mappings for physical to virtual memory. If the virtual address is in KUSAC, the first mapping is simply through page table. Use frame number to find the page number and append offset to the page number. If the virtual address is in ksec0, the second mapping is v equals to the starting address of ksec0 plus p. Similarly, if the virtual address is in ksec1, the third mapping is v equals to the starting address of ksec1 plus p. By the end of this video, you are expected to know what challenges do kernel memory introduce, how do we solve sharing between kernel and user applications, physical to virtual address translation,